Hello everyone, so in this video I want to go over the derivatives of trigonometric functions and do some application problems using these functions. So first I want to go over the derivative of sine graphically. Recall in the previous video we went over the derivative of sine and we even figured out why that is using algebraic methods, but this is kind of to give you a graphical intuition on why this is true. So if we look at our graph, we can see that the top is f of x is equal to sine of x, right? And if you remember from the derivative episode, the derivative of a function is just the slope of the tangent line at that point. So, I don't know, take this point, for example, x is equal to pi over 2. You can see the slope of the tangent line is 0, right? So, the corresponding point on the derivative graph would be pi over 2, comma, and then the slope of the tangent line, which is 0, right? And you could do that for all the points. So for this one, it's 1, right? That's why there would be a point at 1. Same thing for this one, or that's 0. Same thing for this one, right? So you could see that if you use all the slopes, then you actually get this graph, right? And you look at it, well, that has a peak at 0, so that just looks like a cosine graph. And that's how to derive the derivative graphically. Now, you could do the same thing for cosine, and what you'll find is that the derivative of cosine is equal to negative sine of x. And also, just wanted to write, the derivative of sine of x is just cosine of x, right? We just found that up here. Now, we're going to use that to solve this question. This question asks, differentiate y is equal to x squared times sine of x. Now, we know that y prime, from the product rule, which we learned in the last episode, is the derivative of x squared times sine of x. And then we're going to leave the other one, so we're going to take the derivative of sine of x and leave x squared. Now what's this? Well, we bring the power down using the power rule, and then we subtract 1. So we actually get 2x, then times sine of x, plus, well, what's the derivative of sine of x? That's just cosine. So we have cosine times x squared. And this is our answer. Nothing too fancy there. Now, I want to now differentiate f of x is equal to tangent x, kind of broadening our horizons. So how are we going to do this? Well, we don't really see anything, out front, but we know that f of x is equal to sine of x over cosine x. And in the last video, we learned about the quotient rule. And that allows us to take the derivative using the quotient rule. So we have f prime of x is equal to the derivative of the first one times cosine of x, then minus the derivative of the second one, cosine x, times sine of x. And we take the derivative, divide the whole thing by cosine of x squared. Now what is this equal to? Well, the derivative of sine of x is, remember what we saw above, cosine x, and then we have cosine x again. And then minus derivative of here, that's just sine of x. That's negative sine of x. So actually, we're going to move that over here. We're going to have negative sine of x times sine of x. Whole thing over cosine of x squared. And you could probably see where this is going. The top gives cosine squared of x plus sine squared of x, whole thing over cosine squared of x. And if you know your trigonometry, you know that this is just 1. So we have 1 over cosine squared, which is just secant squared. And this is the derivative of tangent x. Now, we could do this for all the other trigonometric functions, say secant, right? Secant is 1 over cosine of x, and you could use the quotient rule like that. And I encourage you to do so. And if you do that, then you'll see that these are the, well, current trigonometric functions and their derivatives. So this is a very important table. You should try to memorize it. I mean, if you have a test, then you could probably derive it as well, but, you know, it'll take more time. So it's good to try to know these off the top of your head. So our first application problem is going to be this one. So we're going to have to differentiate f of x is equal to secant x over 1 plus tangent x. It's asking for what values of x does the graph of f have a horizontal tangent. So what does a horizontal tangent mean? Well, remember, the derivative is the slope of the tangent line. So when it says horizontal tangent, right, that means it's a slope of 0. So that means that the derivative, f prime of x, is going to be 0. So whenever f prime of x is equal to 0, there's going to be a horizontal tangent. And, well, first, to evaluate this, we need to find f prime of x. So let's start off with that. So f prime of x by the quotient rule is going to be derivative of secant times 1 plus tangent, and then minus derivative of 1 plus tangent times secant. Whole thing over 1 plus tangent squared. Okay, so now we're just going to evaluate it. What is the derivative of secant? Well, derivative of secant, we look back. Right, derivative of secant is secant x tangent x. So we can just replace that in our problem. Right, secant x times tangent x. And then, remember, we have to multiply by 1 plus tangent x. Minus, well, let's see. What is the derivative of 1? Derivative of a constant is 0. Easy as that. And now it's asking for derivative of tangent. Tangent, we just solved it. It's just secant squared. So we have secant squared times secant. And then the whole thing is over 1 plus tangent x squared. Okay. So now, we're going to just simplify this a little bit. Right? Just going to distribute the first term. This is what we get. Secant x times tangent squared of x minus secant cubed. Whole thing over 1 plus tangent x squared. And now let's see. We can factor out the secant x from the equation because all the terms have secant. We get secant x times tangent x plus tangent tangent x plus tangent squared of x minus secant squared of x. Okay. Now, if you remember from your trigonometry class, tangent squared of x plus 1 is equal to secant squared, right? Subtract secant squared from both sides. You get tangent squared minus secant squared plus 1 is equal to 0. And then you subtract this from both sides. You get tangent squared minus secant squared is equal to -1. Alright. So we have tangent squared minus secant squared in our problem. So we could just replace that with -1. We get secant x times tangent x minus 1 over 1 plus tangent x squared. Remember, we said we had to set that equal to 0 and then solve for x. So, what do we do from here? Well, first, notice that this bottom part doesn't affect the equation really, right? I mean, how does this denominator affect this being equal to 0 at all? The only way it would is that if this is 0, then it would mess with some of the solutions, right? Because obviously, if you have the whole thing over 0, it's not going to work, right? That's just going to be undefined. So that's the only way it would mess with it, but for the purposes of our video, it won't really affect. So, let's see. We only need to look at the numerator now. We need to see when is secant x equal to 0, because if that's the case, then this whole fraction is going to be equal to 0. And then we have to look at when tangent x minus 1 is equal to 0. So secant x is equal to 0, tangent x minus 1 is equal to 0, right? When that happens, the whole thing is going to be 0. So we're going to have a horizontal tangent. So first, can secant x ever be 0? The answer is no. Because how would you get a fraction equal to 0? You would have to do 1 over infinity, right? And obviously, cosine of x can't be infinity. The highest value of cosine x is 1. So this, it can't happen. But the second one, tangent x is equal to 1, right? I just added 1 to both sides. This works because x is equal to pi over 4 plus pi k. You can look at your unit circle for this to confirm. But now, with this in mind, right, this is the points where there's horizontal tangents. We need to test if the denominator is equal to 0. Obviously, if that's the case, it's not going to work. So let's see if 1 plus tangent of, well, let's try one of these values. Pi over 4 is equal to 0. Right, this is equal to 1 plus, and then tangent of pi over 4 is 1 squared, which is just 2. So the denominator is not equal to 0, which means that this is a valid set of solutions right here. This is our solution set. Now, you're probably asking me, well, why can you just only test pi over 4? Why don't you have to test 5 pi over 4, for example? Well, the reason is because tangent of x repeats every pi x values. So you don't really need to test it because right now our period is pi for the repeated solutions, and this period is pi. So if you think about it, right, it's just going to give the same value. It won't affect anything. So the denominator is always going to be 2 for the solutions, and therefore it's going to give a valid solution. Now, the next problem, I'm also going to just move this down a little. Next problem is asking, if f of t is equal to secant of t, find f double prime of pi over 4. Not as bad as the last one. We're just taking derivatives here, right? So f prime of t is, f prime of t is going to be secant t times tangent t, right? From the table. Now, what is f double prime of t? Well, that is going to be, we're going to have to use the product rule for this one. Derivative secant t times tangent t plus, then we're going to do the other one, derivative of tangent t times secant t. That is going to be equal to secant t times tangent t again, plus secant cubed of t. Remember, I just condensed that. Nothing too fancy there. Again, that's just equal to secant t times tangent squared t plus secant cubed of t. Okay. So now we could just plug in pi over 4 into our function, right? First, let's figure out what tangent of pi over 4 and secant of pi over 4 are, so we could, have this easy. Tangent of pi over 4 is sine pi over 4 over cosine of pi over 4. That's just 1, right? Because the numerator is square root of 2 over 2, the denominator is square root of 2 over 2. So that's pretty easy. Secant of pi over 4 is 1 over cosine pi over 4, which is equal to 1 over square root 2 over 2, which is 2 over square root 2, and then we could multiply both the numerator and denominator. This becomes 2 square root 2 over 2, which becomes square root 2. All that process was just to simplify it, right? So it's not too complicated. So plugging this in, right? This is asking for secant of pi over 4 in the first spot, which is square root 2, then times 1 squared, plus this one cubed, square root 2 cubed, which is square root 2 plus 3 square root 2, 2 square root 2, which is 3 square root 2. And this is our answer right here. Right. So derivative is just a lot of work, but not too difficult in general. This problem's, more of an application problem. So let's just take a look at it. A ladder 10 feet long rests against a vertical wall. Let theta be the angle between the top of the ladder and the wall, and let x be the distance from the bottom of the ladder to the wall. So what's it saying? Well, I'm just going to draw a diagram really quickly. That's a right angle. The ladder, this is the ladder, rests against a vertical wall, and the ladder is 10 feet long. And theta is the top of the ladder and the wall. So the top of the ladder is right here, and then the wall is right here. So this would be theta. And it's saying let x be the distance from the bottom of the ladder to the wall, right? So this is x. Now it's saying if the bottom of the ladder slides away from the wall, how fast does x change with respect to theta when theta is equal to pi over 3? So whenever it says how fast does x change with respect to theta or something along that lines, it's talking about a derivative, right? Derivative with respect to theta. So the first step to solving these types of questions, we're going to be looking a lot at this at our section of related rates, but this is just an introduction. So the first step to these types of problems is to look at a relationship between the variables. In this case, we could see that sine of theta is equal to x over 10, right? Okay, so now we found a relationship. The second step is either manipulating the variables somehow or taking the derivative. So in this case, we need to manipulate the equation a little because it's saying how does x change with respect to theta? And what does that mean? Well, that means that's talking about d over d theta, derivative with respect to theta of x, right? Right now we can't just do that because we don't have our x by itself. So we have to get the x by itself by multiplying by 10. This gives you 10 sine of theta is equal to x. Nothing too complicated there. And then we can just take the derivative of both sides with respect to theta. Okay, so this gives dx over d theta is equal to 10 times, and then derivative of sine is cosine. So now we have our derivative function. It's asking for what's the derivative when theta is equal to pi over 3. So let's plug in pi over 3. Dx over d theta, and then we use this to denote theta is equal to pi over 3, just to show where we're evaluating at 10 times cosine of pi over 3. That is equal to 10 times 1/2, which is just 5. And what is our units? Units are, well, let's see, it's talking in units of x over units of theta. X, remember, is feet. And then units of theta, if it doesn't say specifically it's degrees, it's always radians. So it's 5 feet over radians. And this is our answer. Anyways, if you enjoyed this video, don't forget to like and subscribe. And let's do some more math in the next video. See ya.